Watch as Zoe jumps over this 1 meter high obstacle.
Together, Zoe and her horse have a mass of 625 kilograms.
We will be examining this from an energy lens and using that to calculate the horsepower of Zoe and her horse. But first, let's jump into tracking. Wow, that was crazy. Now you'll notice red diamonds on the horse. Each one of these holds an X and Y position of the horse. We've chosen to track a very specific point on the horse's saddle, and this is because we have deemed that it moves up and down less than the other points on the horse. Now you'll also notice blue diamonds and pink diamonds to the left near the meter-high jumping point. These are to track the calibration stick onto that meter-high jumping point. The calibration stick has to be tracked onto this meter-high jumping point because the camera pans. The point of the calibration stick is to tell Tracker what is a meter, and it can use this to decide where the horse is. Just below this calibration stick, you will also notice a grid with pink lines extending far in the left, right, up, and down directions. This is to let us know where the horse is in the world. Currently, the horse is in a positive direction on the x-axis and a positive direction on the y-axis. You'll notice that the horse and its tracking point are already more than a meter high. Now, as the horse jumps over the meter-high jumping point, that it will then be moving in the negative direction. This was something we had to account for in our data, and we had to manipulate it in order to always show a positive movement on the x-axis. As we examine it from an energy lens, first we notice that it has reached its maximum kinetic energy about here. Zoe and her horse are moving at 3.5 meters per second, and the horse weighs 625 kilograms. This means that the horse and Zoe have a kinetic energy of about 3,800 joules.
Take a look at this position versus time graph. As you can see, the velocity will remain mostly constant. This means that for the rest of our calculations, we can use 3,800 joules as our kinetic energy.
You will now notice the horse has reached its peak.
As we saw from the previous graph, the kinetic energy will still be 3,800 joules. Potential energy is equal to mass times gravity times height. Now the change in height here is only 0.8 meters because the horse, from where we were tracking it, already had a height of about 1.4 meters. Furthermore, the mass of the horse and Zoe is 625 kilograms, and the acceleration due to gravity is 10 meters per second squared. Therefore, the potential energy is 5,000 joules, and the kinetic energy plus potential energy is 8,800 joules. Work equals change in energy, and the change in energy of the horse at the peak of its jump from when it started pushing is 5,000 joules. Now, power is work over time, so we need to find the time that the horse was pushing so that we can calculate its horsepower. From this extremely slow motion video of the horse jumping, we can see it is pushing on the ground for about 0.2 seconds. Having stated previously that power equals work over time, we know that the work is 5,000 joules and the time is 0.2 seconds. 5,000 joules divided by 0.2 seconds is equal to 25,000 watts. 1 horsepower is equal to 735.5 watts. Now, that means we have about 34 horsepower.
The horse lands. Now that we have seen our data, let's see what it implies, and if we made mistakes, where could they have occurred? This shot was filmed with a wide-angle lens. As a result of this, there is distortion around the focal point. Tracker does not incorporate this into its calculations, so this is another source of potential error. Furthermore, Tracker is not perfect with its tracking. This means that sometimes the velocity can change very rapidly. This could easily lead to errors when calculating kinetic energy. Since we are benevolent students, we decided to leave you with cute videos of Zoe's horse Premier. And remember, we love A's as much as Premier loves carrots. The end.